Welcome back to compiler construction. In today's lecture, we'll take a look at procedures and functions and how to implement them. So we'll take a look at procedures, how they are encapsulated and what they encapsulate. They are a basis for structured programming, and they provide an important abstraction for code that we write in a programming language and in turn for code that's generated. And then we'll talk about keeping data and related information on the stack for procedures, so-called activation records. So procedures or functions were introduced to give programs a structure. So far, we have only considered sequences of instructions, and very early programs for computer often were very unstructured. So they only provided functionality for global variables. You had to repeat code whenever you wanted to repeat a functionality, and this was the common source of many program errors. For example, reusing a global variable in a different context and overwriting its value while another part of your program accepts the value to be the same, or changing one of the repetitions of your code, but you forget to change one of the others to fix a bug, for example. So very early on, an idea to give structure to programs was to introduce some sort of hierarchy. So a program was split into so-called procedures, and a procedure is not only a name for a piece of code, but a procedure has additional properties, so it provides a scope for the names of variables, maybe also for the names of functions, and so on. So let's take a look at this example here. So this would be just a C program without any functions, and this C program should actually calculate the sum of the lengths of two strings. So we have an integer variable for the length of our strings. We have two pointers to character arrays A and B here, and then we could implement this like while the character at pointer location A is not 0, we increment the pointer and we increment our counter, and we do the same for string B down here. Now, this is a bit tedious, so here we're repeating code, and this code should be better encapsulated, with the advantage that we actually got a glimpse of what this line of code is doing. So what we would usually do is we would encapsulate such a functionality in its own function. We can give it a meaningful name like string length here, so we can tell the input and output parameters. So string length receives a character pointer as an input and returns an integer, the length of our string. And then we can actually put this line from here over here to calculate the length of our string and return it. And now in our main program, we can just call string length for string of A and string length for string B, add the both integer values that are returned together, and assign them to our variable x. So that makes our program easier to read. It encapsulates things like our length variable here, so we don't need to know as a user of this string length function what's actually happening inside of that function. We only need to be able to call it and read the result value. So as an example, let's take a look at C functions here. So a side remark is that some languages actually distinguish between functions and procedures. For example, Pascal does this. So a function is some subprogram that returns a value, whereas a procedure is a subprogram that doesn't return a value, but it takes a number of values. So if we take a look at our example here, we see we have a function. This function has a name, mult for multiplication here, for example. It has a return type, so it returns a variable of the given type, an integer here. And in our brackets, we have our parameters. So here we have two parameters separated by a comma. The first one is an integer we call m inside of that function, and the second one is an integer we call n inside of that function. Altogether, this is our function signature or our function header. So after our function header, our function body or implementation starts. And in this implementation, we can have local variables here. So we have a block of C code indicated by the curly brackets here. So we can declare local variables here, which are only visible inside of that block. We can call ourselves recursively here. So inside of mult, we can call mult again. And we can return a value from the function. So whenever we got our result finally calculated here, we can actually tell our function to return the result, which means that this value of that variable here is returned as the integer return value of the multiplication. And then you can call this like here, and you can use the function call as well as a normal variable or number in an expression here. And you can pass any local variable or constant as parameters here. And our compiler takes care of copying the value of that variable x that we pass over to our local variable m, and copying the value of our variable y, that's our second parameter, over to local variable n. So we call this function invocation, or multiple function invocations, also the call side of a function of the function mult in our example. So procedures are programming abstraction, and this abstraction is used to make the development of large software systems practical and possible. And to do this, it applies a number of principles. So the first principle is information hiding. Information hiding means that the structure and content of data objects that are used inside of a procedure are hidden from the rest of a program. So for example, I can't see what's going on inside of a procedure, unless I have the source code, obviously. And more important, I cannot get any access to local variables inside of my function. And this is important because then I can ensure that only my function itself can change its local values. In addition, a function provides distinct and separable namespaces, so we can have variables inside of a function as local variables that have the same name as a variable in another function, or even as a variable which is a global variable here. So these names would cover the other uses of these names outside of a function. So this means data objects used inside of a procedure or function do not interfere with identically named objects of other procedures or on a global scope. The third advantage we have by using functions and procedures is we have uniform interfaces. So procedures provide some sort of a pattern to model the access to data. So we cannot just write over global variables and then have some code executed to work with the mess we generated, but we know we can, for example, provide access only through a given parameter, and we can check the values of this parameter and so on. In most architectures today, there is no hardware support for implementing procedures. This was something that was experimented with in the 1960s, 1970s, and nowadays mostly compiler writers have to generate code to realize procedures by hand, and since procedures are such a common abstraction, the compiler has to take care of providing an efficient implementation for this. So let's first take a look at information hiding. Information hiding means the structure and content of data objects used inside of a procedure is hidden from the rest of our program. So let's take a look at our example. We've already seen we have a local variable result here, which is an integer variable. And if we actually tried to access result in main, what we do here is we have a local variable result in main. So if we use result in our main function, we would access this local variable in main here. Whereas if we access result in our mult function, we would access its own local variable here. So the type and the name of this local variable result here are not known outside of our mult function. So this means even though we have an integer variable result here in main, we don't have a clash, we don't override this result with values we would assign here. So main or other functions cannot access the value of our local variable result here inside of our mult function. Namespaces are distinct and separable, so data objects used inside of a procedure do not interfere with identically named objects of other procedures or on global scope. So we've already seen this with a result, and the code inside of mult, as we've seen, cannot see this variable result of main in turn. So we have result here, and we have a result in main, and the other way around. Now this mult function cannot access this result variable in main here. So what happens here is what we call lexical scoping. So it means that the scope, so the area of a program in which a variable is valid, is restricted to its enclosing function here in this case. So for example, in this main function. To be more precise, it's actually inside of our curly brackets here. So if we had additional curly brackets, like for example the loop body of a while loop, we would have an additional lexical scope, and if we declared a variable inside of a loop body, it would only be visible inside of that loop body. Now, what happens with recursion in namespaces? So as we've seen, a function is able to call itself. So the mult function here can call itself with different parameters. So for programming languages that allow recursion, so such as C, we have to ensure that every separate invocation of a function has its own copy of local variables. So if we enter mult for the first time from main, we have a copy of result, and if this mult function then calls mult recursively again, we need a second copy of result for the second invocation, because otherwise we would overwrite the initial result value of our first invocation here, and after return we would have the wrong value in result. So essentially the compiler again has to take care of the fact that this has to be kept separate. So for each recursive invocation, our compiler has to ensure that we have our own copy of local data. Procedures also provide a way to structure the control flow. So a procedure has a well-defined control flow. We know that a procedure is invoked at a call site. Like here, we invoke the procedure P, and we give this procedure P 3 defined parameters, so a constant 10, and two variables T and U, which have to be defined inside of the context at the call site. So this changes execution to this function here, and it takes care of copying these parameters over. Then this function starts executing. This might execute the call to a different function, to the function Q, passing parameters C and B to it. So we execute function Q. Function Q might call itself recursively a number of times, and ultimately function Q will not only return from its own recursions, but also return from its first invocation by returning a value here, which we can then use in P again, and eventually P then returns to our initial call site here, and we can use the result and assign it to a variable and continue after the original invocation of P. So control returns to the call site immediately after the invocation of a function, so usually in the next line of code or in the next part of your expression, depending on where you actually invoked the function, in which context you invoked it. A function usually has multiple call sites, so we can not only call a function from this one place, but from an arbitrary number of places in our code. This means we always need to remember where to return to. So if we call P here, we need to return to that location. If we call P somewhere else, we need to return to this other location. And most languages allow recursion, so this also has to be valid when a function recursively calls itself. So when we want to implement procedures that have this behavior, we need code to save and restore this return address. So when we call P, we need to remember somewhere where to return to when this function P returns. When P calls Q, we also need to remember where to return when Q returns, so to this location here. And of course, when Q calls itself, we also need to remember where to return to when the recursive invocation of Q actually returns. So we need to save and restore return addresses for every function or procedure invocation. In addition, we must map the actual parameters to formal parameters. So the actual parameters for our invocation at this call site of P would be 10, T, and U. So our compiler has to generate code that ensures that this value 10 is copied to our formal parameter, which is A. This value of variable T is copied to variable B, and this value of variable U is copied to variable C. And of course the same for invocation of Q. In addition, our compiler must take care of creating storage for local variables and maybe also our parameters here for each invocation of a function here. So we need space for a local variable d here, for example, inside of p, and maybe also a, b, and c here. And we need it for every invocation of p, since we don't know if somebody else is going to invoke p later on. So maybe q would invoke p somewhere. We also need to provide this even if we don't have a direct recursion inside of p. So the question is, where does this space go in our recursive invocations of functions? So in a general way, we can say that we have to preserve the state of function p, including its parameters and local variable and the location it was executing, while q executes. And q can execute multiple times because it calls itself recursively. So the real problem here is caused by this recursion, and the strategy to ensure that we have local copies of all our parameters and local data is to actually create a unique location for each procedure activation. And it's very common to use a stack of memory blocks for this, and each of these memory blocks holds local storage here for our variables, for our parameters, and the return address to indicate where to return to when our function is terminating. So which tasks does a compiler have to perform when it wants to implement procedures? Now first, it has to do a number of things at compile time. So it needs to determine the memory locations for each of the variables inside of our functions. It has to map each variable to its lexically correct scope so that we can ensure that when we use a name in our function that it's actually the correct variable that's accessed. Our compiler also has to ensure the mapping of these actual to formal parameters, as we've seen. So it has to copy the parameters that are used at the call side to the parameters which are named in the signature of our function. And of course, it has to generate the code implementing the function. But that's not all, because when we call a procedure, we need to ensure that all these conditions are held, so that we have a local block of memory to hold our local variables, that we store our return value, and so on. So at runtime, we need to execute a number of things. And in order to be able to do this, our compiler has to generate code for this at compile time already. So in addition to the code that's actually the function you've written, our compiler also generates code to create space for the storage of procedure-related data, usually when you enter a function, before you execute the very first instruction you wrote yourself for this function. It also creates code to store the return address. It creates code to copy the parameters into appropriate memory locations. And finally, of course, when we call a function, it needs to generate code to change control flow to the procedure or function we are currently calling. So where do we actually store all this local data for a function invocation? So parameters, local variables, and return address. Now the data structure to do this is a so-called activation record here. So an activation record here is created for each invocation of a procedure or function, and this contains a space for the parameters for the current routine, so where the actual parameters are copied to our formal parameters, so we don't change the actual parameters at the call side, which would be fatal. We might want to save processor registers because our compiler and CPU assumes that at least some of the registers still contain the old values when we return from a function. So we might need some register save area. Which registers exactly to save is described in the so-called application binary interface. We need to reserve some space for a return value for a function. We also need to reserve space for the return address, so we know where to return to when our function terminates. We might have some support for accessing non-local variables here, which we call addressability. And then finally, our pointer here, our activation record pointer, points into the middle of it. So all of this information on top here was actually generated when the function was invoked, so usually by code that was generated automatically by the compiler and stands at the beginning of a function. And then we can also have a pointer to an activation record here, so we point back to a previous activation record of the function that called us, And finally, we can have a set of local variables here that can grow rather big. So local variables and a pointer to the caller's activation record are actually stored below our own activation record pointer. So we could actually walk up the hierarchy to the function that called us, to the function that called the function that called us, and so on. So how does our compiler actually find the variables that are part of our activation record? Now we've seen that our activation record pointer here points into the middle of our activation record, and below this activation record pointer we know we have stored our local variables here. So the compiler has to figure out the space each of these variables actually uses, and then the compiler actually has to remember this offset, so it has to sort our local variables in some specific order here. And then for each of these local names, it has to remember not a global address here, because these are only relative to our activation record pointer, but it has to remember an offset now to our activation record. And this offset is often used very efficiently because many machines, many processors have a special machine instruction load indexed that can load data from some pointer in a register, and you add a constant value, which is the offset of that variable, to that pointer, and you can do this in only one machine instruction. So this means accessing local variables can be very efficient here. So the level of on the stack specifies an activation record pointer, and the offset here is our constant. Now we can also have variable length data. So if we allow our activation record to be extended, we should put it above local variables here, and then leave a pointer at a known offset from the activation record pointer. If we won't allow for this, we could also enable our programming language to just put variable length data on the heap. Now finally, our compiler needs to be able to initialize local variables, so it needs to generate explicit code to store the values of local variables here, and this is again one of the first things a function or procedure does when it's invoked. So here's an example for an activation record. We see the general structure of an activation record here, and this is already filled in with the values relevant for our function p. So this is our function p again, taking three parameters a, b, c, and it has a local variable d, and it calls a function q somewhere in its flow of execution. So when the execution has arrived at function p, a local activation record is created here for p, and this contains first the values for our parameters a, b, c. So the actual parameters have been copied into our formal parameters a, b, c, which we can use as a local variable here. Our processor registers that we need to save are saved. Also our return value for returning to the function that has called p is saved. Now our return address is saved. That was that. Also, we have reserved space already for a return value we want to return from p. And we have our activation record pointer here. And now on our activation record, we also have a pointer to our caller's activation record. So this is somewhere further up in our stack. And we have space for our local variable d. So we only have one local variable here, which is allocated in our space for local variables below the pointer to our caller's activation record. So what happens when p now calls our function q? So at this point in time, we know that we need another activation record here. So our code that is generated by the compiler and is somewhere here at the beginning of Q, of course invisible because it's only automatically generated code. Well, this already has provided functionality to add a new activation record to our stack, and it has copied our values of variables c and b here to our formal parameters x and y, which we can use as local variables. It has saved registers here. It has provided space for the return value. It has saved the return address, so the address after the invocation of q and before the allocation here to our variable d. This return address has been saved in this location here. And finally, we have our pointer to our caller's activation record, added here. So what is happening is that the activation record pointer, which is usually one of the processor registers, is actually first saved here before we then overwrite it and set our new activation record pointer for procedure Q to this location here, so pointing to its own activation record. And we need to do this because when we return from a function, we not only have to restore the correct location in the control flow of the function that has called us, so in this case here before the return to Q, but we also have to restore the activation record pointer, so when we're back in Q, our activation record pointer points back to the correct activation record belonging to P and no longer to the one belonging to Q. And this is important because we will need to use this activation record pointer, for example, to access variable D, in which we are going to write the result of our function invocation. So after the execution has returned from Q, Q's activation record is no longer needed. So this activation record can actually be removed from the stack, but we need to do some additional things. So we have reserved memory for our return value. This has to be copied over, in this case to our local variable D here. And finally, the activation record pointer needs to be copied over. So essentially, by setting the activation record pointer to this location for the activation record of P, we have automatically invalidated the activation record for Q because no activation record exists below the one we are pointing to. However, what does not happen is that this activation record for Q is somehow removed from memory. So it's not zeroed or overwritten with some random values or something else. It simply stays in memory because we have an indication by setting this ARP back up here that everything below here is invalid. So essentially we save overhead for deleting this activation record here by just ignoring it when we return from our function Q. So how do activation records work when recursion is used? So what happens here when Q recursively calls itself? Now, it's actually the same as with every other function call. So when we are in Q, so the first invocation of Q from P here, we call Q again, and this again just creates another activation record. Again, one for Q, but that doesn't really matter here. And we could create yet another one, and so on until we run out of memory. So for each new level of recursion, the code at the start of our function that's generated by our compiler before our very first instruction we wrote ourselves takes care of allocating a new activation record here and automatically removing it when this invocation of the recursion is actually terminating. So if you have too many recursion levels, you can get a stack overflow here, as we've seen in our C programming examples before, and this means we just ran out of memory because we maybe have several millions of recursive invocations of Q on our stack, and we don't want to provide enough memory for this. So this was a quick overview of how functions or procedures work in common programming languages. There are a number of optimizations possible we have not talked about. So for example, for the very last invocation of a function, so the one that really returns instead of recursively invoking itself again, we could save overhead, for example, for these leave functions here, and do something we call a tail call optimization. So if you're interested in that, let us know, and we can provide you with reference to this. So this is very useful when you have very many recursive function invocations, especially in functional languages, like for example Lisp. It's sometimes done by compilers for C also, but it's not too common, at least in older compilers. So what's next in our course? Now, we're finally almost at a point where we can generate machine code. So we have generated an intermediate representation from our abstract syntax tree, which was generated by parsing our input, which was supported by scanning our tokens. So now we need to choose a target machine. And this target machine is a very common one. So we use 64-bit Intel or AMD processors, which most of you probably have at home. We can also provide you some links to 64-bit ARM assembler programming in case you want to use it on a Raspberry Pi or maybe one of the new Macintoshes. But in general, we'll use x86 machine language, assembly language for now. So the next thing we're going to do is we'll provide you with an introduction to assembly programming on x86 in 64-bit mode, and we'll also show you how a procedure looks, what a procedure looks like in real life on a 64-bit x86 architecture. And one reference we should definitely give here is the reference to a very famous letter to the editor of the Communications of the ACM journal by Dijkstra himself in 1968. And he was a very strong proponent of this structured programming approach with procedures and functions. So to split up your program into smaller parts which are easily manageable. And before procedures and functions, you use the goto statement, like in our intermediate representation or in assembly language, to just switch control to an arbitrary point in your program. And this caused what people nowadays call spaghetti code, because if you look at the control flow diagram of such a program using just gotos instead of ordered function calls and returns, this looks just like a plate of spaghetti. Essentially, this was really going on the nerves of Dijkstra, and so he wrote a letter to the editor. Goto statement considered harmful, and this is one of the classic reads in computer science, and I can only encourage you to read this short bit of code to see which problems people had using computers more than 50 years ago. So that's all for today. Thanks for listening, and until next time. Bye.